this in context. Think what we've talked about in this chapter, chapter 5, right? We've been talking about graphing motion. We've become more familiar with what we're going to call the kinematic quantities, position, velocity. Today we're going to extend that and talk about acceleration. We talked a little bit about it, but we're going to talk more about it. So, we got time, right, which sort of knits all this stuff together. Position, velocity, acceleration. Okay, we said some stuff earlier about velocity and position, about how they're related. So what we say, how are velocity and position related? And isn't it great how this goes right along with the calculus we're talking about? It's exactly in sync with where we are in calculus. Okay, good. So velocity, the velocity of an object is equivalent to, or can be found by, taking the slope of a position time graph. That's one way to think about it, right? In calculus, we're now saying that velocity is the derivative of position, right? We can say in calculus or in physics that velocity is the rate of change of position, because rate of change just means a slope, right? That's all a slope is, rate of change. Okay, so then we said that if we look at the velocity of, for any value of t that we choose, if we draw a tangent line, right, and we find the slope of the position time graph, that gives us the value of the velocity time graph, right? And then we went on and we did just a really short assignment about velocity time graphs. And on the velocity time graphs, there was something unique about that too. What did we say about the area under a velocity time graph? What's that equivalent to? The total displacement, right? Right. And we haven't done a lot with that. We'll get back to that. Okay, so let's start off then. Let's just add a definition. So we know that velocity equals the rate of change. So delta d over delta t, right? And we know that, and we're talking about averages, aren't we? Average velocities is delta d over delta t. What about acceleration? Do you remember what that is? What's acceleration? Delta d over delta t, yeah. So right away we can see that there's this kind of parallel relationship, right? We can say that it's like those analogy questions. A is to V as V is to D, right? Does that make sense? Okay. So if we were to do something then, like let's take, notice what I've done here. I've just got a position time graph. Right beneath that's going to be the corresponding velocity time graph. Right beneath that's going to be the corresponding acceleration time graph. So if this is our position time graph, can anybody tell me here, what's going to be the basic shape? We don't have any numbers up there, right? So we can't really be too precise, but what's going to be the shape of the velocity time graph? It's going to be a horizontal line. Good, okay. And what about the horizontal line? It can be a little more specific than that. It's going to be positive, isn't it, right? The slope of this blue function is constant and positive, right? The slope is constant and positive. So we get something, everybody agree, would look basically like this, right? Constant and positive, okay? So then, Alyssa, what's going to be, I'm going to challenge you, what's going to be the acceleration time graph? What do you think that's going to look like? Now keep in mind, we said that A is to V like V is to D, right? So velocity, the value of velocity equals the slope of the position time graph, right? So what do you suppose the value of acceleration is going to be?
I'm not sure.
Okay, let me say it again. You'll get it. So the value of velocity is given to us by the slope of position, right? So we said that because this function has a slope that's constant and positive, that meant that the velocity had a shape that was constant and positive, right? The value, not the slope, but the value, right? So if I want to go down here then, the value of acceleration must be related to Slope. The slope of the velocity graph, exactly. What's the slope of that graph?
0.
0, sure. So then, this is the acceleration time graph, isn't it? It's just got a value of 0 everywhere. Make sense? Okay. Questions? Okay. Let's do another. What about something like this? Take a second. Think that one over. What do you think? Suggestions? Ideas? What do you think, Elijah?
First will be like really steep
Okay.
line.
Okay.
And then flat, and then steep in the negative direction.
Okay, you want to drive?
Sure.
Put you on the spot. Okay. Does anybody want to? Does anybody want to modify that a little bit? What do you think? What, modify?
Just erase the whole thing and then draw a line.
Okay, what kind of line? I'll do exactly as you say. We'll,
It's easy to go draw.
A positive slope that starts. Actually, no, like it's a negative slope.
okay, so.
And then it enters 0 about where the vertex of gravel is.
Okay, so now that's a good observation. We don't know, there's no numbers up here, right? But there is one slope that we know for certain. Where's that? The vertex, the horizontal tangent line, right? So right there, where we've got a horizontal tangent line, we know that this has to have a 0, has to have a 0 value, right? Okay, and so then you were telling me it goes like this, is that right?
Other way.
Other way, good, because it starts with a
Positive.
steep positive slope. It gets less steep as we move along, goes to 0, and then it gets more negative as we continue to the right. So it starts very positive, gets less positive, goes to 0, gets increasingly negative. So doesn't that sound like that? Agree? Does that make sense, Elijah? Does that make sense?
Yeah, I get it.
Okay. Right? Okay, so then what about the acceleration time graph? Olivia, what do you think? So that's got to be, remember, the slope of the blue gives us the value of the red, right? I should say the slope of position gives us the value of velocity. So the slope of velocity gives us the value of acceleration. What can you tell me about that slope? Negative and constant, right. So what's this going to look like? How do I draw a function that is negative and constant? Think of like y equals -5. That's constant and negative, right? So it's going to be, what's it going to do? It's got to have, the slope is constant and negative. So the value every place on the acceleration graph has to be constant and negative. So the value's not going to change. It's going to always be negative. The same value, too. So what would that look like as I went from left to right? Okay, so I hear it like that, right? Does that make sense? So the value, we don't know what the value is because we don't have numbers to calculate that slope. But let's just say hypothetically that the slope was -5. Then the value of acceleration would be -5 everywhere. Okay, make sense? You got that? So let's look at this in terms of a story about what does this story look like if we start at the top and work our way down. Let's look at the story from each perspective. And in a way, what you're going to see is that the story gets a lot easier to tell, maybe more boring to tell, as you work your way down. Okay, who wants to tell the blue story? What's going on with the blue story? I'll just, in terms of my walking in a straight line along the front of the room. Where do I start?
The negative.
Negative position, right? And what am I doing at the time we start the stopwatch? Well, I'm going pretty fast, aren't I? My velocity is large and positive. So when we start the stopwatch, I'm cruising through right here, right? I'm at a negative value going pretty fast. What's happening to my velocity? So the first half looks like this, doesn't go fast, slow down, come to rest, right? Now what? And pick up speed in a negative direction, faster, 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 and then I'm off the screen, right? Make sense? Okay? Does that make sense in terms of my velocity? It does, doesn't it? All the velocity graph tells me is I'm starting off with a high positive velocity, it's getting lower and lower and lower, 0, negative velocity increasing, right? Getting more negative, okay? Now, can you reconcile that with the green graph? Alexa's shaking, she's saying, yeah. How are you going to do it?
Just because we want the same speed the whole time. Well, except for the first one. Just kidding.
No, you're onto something. You just used the wrong term. You said I'm going the same speed the whole time.
No, it's the same. It's acceleration.
It is, right? Now think about how we've always talked about acceleration, right? Acceleration is just the rate of change of velocity. That's our new way of maybe talking about it, right? Velocity is the rate of change of position. Well, what's the velocity? How is it changing? Is it changing in a positive or negative way?
Negative.
It's getting more negative, isn't it? Right? So that means if the acceleration is what describes how the velocity is changing, then the acceleration must be negative, right? So if the acceleration is negative, it's trying to change the velocity in that direction. Remember us talking about the invisible hand. In what direction? Now think about the story from the beginning. If I start here and I'm cruising really fast in this direction, in what direction is the invisible hand pushing on me if I'm slowing down? That way, isn't it? That way, slow down, still that way, because now I'm speeding up in this direction. Does the invisible hand ever change? Same way the whole time, isn't it? It's always pushing me that way. Would you agree that as far as acceleration is concerned, slowing me down in a positive direction is really the same thing as speeding me up in a negative direction? Right? Make sense? Okay, I'll tell you another version of this one right now that's maybe easier to understand. Let's take the displacement, or excuse me, the position. This time, instead of it being horizontal in the front of the room, let's make it vertical up and down. And let's say that the 0 is going to be right here. So this is 0, right? Everything above this is a positive vertical position. Everything below it is negative. Here's another way of telling that story. Oops, missed it. I'm looking. Shouldn't know what catch. You see how that worked? Right? You ever see that? It started off with a fast, moving fast in the positive y direction. But what did it do? Let's take this in slow motion. It was going really fast. It slowed down, it slowed down, it slowed down, it slowed down. What did it do right there?
Stop.
Okay, it came to rest. Well, did it really come to rest? I mean, its instantaneous velocity was 0. How long was it 0? No time, right? It's just all the 0 is there is just the boundary between going up and going down, right? Okay. So 0, and then it got more and more negative, right? Now, did the acceleration on this thing change? Did it? It didn't. What was the only force? Because we're going to soon learn that force and acceleration are joined at the hip. Force is what's responsible for acceleration. We'll get there next chapter. But what's the only force acting on this thing the whole time? It's weight, the force of gravity, right? None of that changed. So the acceleration was constant. What we're going to find out here real soon is that anywhere near the surface of the Earth, the acceleration of gravity is roughly constant. It's about 9.81 meters per second squared down. So we give it a negative sign because it's pointing in the negative y direction, right? It's really more of a pseudo constant. It's not actually a constant. How come? Well, it rotates, but that's not why.
Or because it only applies to where,
Say it again?
if that number only applies to close to it. That's
Well, sure, but even if I were even walking on the surface of the earth, there are certain places where I might experience a slightly different acceleration due to gravity than others. Okay, yeah, like, for example, if I'm above, well, for one thing that might be even easier to understand is, what if you climbed a tall mountain? What are you doing to your distance between the center of the earth? You're increasing it a little bit, aren't you? So you'd expect that maybe you're gonna get a little bit less gravity on top of a mountain. Now, it turns out that oftentimes mountains are made of pretty dense stuff, and so maybe you don't see that so much. But if you were walking even on a relatively flat place, like around Pendleton, Pendleton sits on top of a geologic formation called the Columbia River Basalt Flows. Very dense rock, very dense rock. So we are gonna be a little heavier in Pendleton than you would be if you went to, say, Cannon Beach or something on the coast, where you're gonna be standing on top of a relatively low-density rock structure, it's just mostly sandstone. And so you'd actually you wouldn't notice it, but if you measured it with a microaccelerometer, you would see that there's a little bit of a variation in the strength of gravity there. You're gonna weigh a little bit more here than you do there. And so you can do that. You can actually map out the local differences in the strength of gravity, and it's you can actually kind of get some sense of what's below the earth by doing that. Yeah.
Would it be like sort of noticeable if you were like at 0 feet sea level on like really dense rock and then went up to a mountain there?
It would be, the difference is, and here's why. It seems like it ought to be more, but if you look at the Earth, what's called the aspect ratio of all the features on the surface of the Earth, and when we talk about an aspect ratio in physics or engineering, what we're really doing is we're talking about the relative size of things, right? So mountains look pretty big to us, right? Because we're small and the Earth is big from our perspective. But the Earth is quite a bit smoother than a billiard ball if you look at it from the perspective of far away in space. So those big mountains, think what a big mountain is. I mean, a big mountain has relief of, like the Wallowas are actually, if you go from Joseph up to the top of Chief Joseph Mountain, that's big relief. There are very few places where you can see that much vertical relief in a mountain range, and that's about a vertical mile. Okay, so if that's a vertical mile, so say that's about 1 point, what would that be? 1.3, 1.4 kilometers, something like that. So about that many thousand meters. The radius of the Earth is about 6 million meters. So you're looking at a relatively small, that's not much. That's a very, very, very small little bit compared to the vast distance between the surface of the Earth and its center, right? And so you really don't notice very much of a difference. It's so small. And usually that's offset a little bit by the fact that mountains usually have a little denser rocks. So you don't notice that much of a difference. You really don't notice that much of a difference. Probably where you notice the biggest difference would be if you were right above a really deep part of the ocean, because water is significantly less dense than rock. So, but even then, you could never notice it. You'd have to have a really sensitive instrument to even be able to read the difference. But it's kind of interesting. So it's, we call it a constant, but it's not really. It's a pseudo constant. It's just roughly 9.81 any place you're going to go. Okay. But that's interesting that this is the story that we tell, right? I mean, the acceleration is the same, right? It's constant, and yet we get pretty widely varying velocities and positions, right? Okay, now this is what's really trippy here. Listen to this one. So we told a very specific story about starting here and getting to here. And we got the right answer. There's only one right answer that we could have gotten. This blue position function exactly corresponds to this red velocity function. Assuming, what was that? Timed out? Wow. I don't remember ever doing that. Oh man, did my computer just restart? No, it didn't. Okay. So the blue curve gave us one answer, that's it, for the red line. Then the red line gave us one answer for the green line. Let's reverse the process. Let's start again. Let's say we start with the green acceleration function. Can somebody draw, so now we're gonna go bottoms up. If we start at the bottom and work our way up, that's an answer for what the velocity could be. Can somebody give me another one? What do you think?
You seem to think it's just higher or lower.
Ah, yeah, because the slope doesn't change if we offset the function vertically, does it? How about that? So I'll draw them maybe like an orange, so they're like the original one. What if we did that, for example? That's a different story, isn't it? It's quite a different story. This one here, let's tell the red story for a second. The red story, we started off going really, I was going really fast at the start of the film, right? We start the stopwatch, I'm going pretty fast in this direction, and I slow down, and I just come back. Now the orange one, what am I starting at?
0.
I'm at 0, aren't I? Right, so I'm starting, it doesn't tell me where I'm starting. See, I start here. I start at rest, and then I just pick up speed in this direction, right? Weird. Very different stories, right? Or are they so different? If I continue those lines out, like if I were to continue the orange line back in this direction, and really all I'm doing there is I'm just going to a time earlier than when I started the stopwatch, it looks very much the same, doesn't it? Right? Everybody agree? Interesting. To me, that's interesting. That when you move upward from the bottom, you get this, you can't get an exact answer. There's an infinite number of different curves we could draw that would give us that result, right? Let's even go further with it. What about the red graph corresponds to the blue graph, doesn't it? Okay, but even if that's the red graph, could I draw other blue graphs that go with that, with just this red graph? Sure. Sure I could, couldn't I? Couldn't I just, any one of those blue graphs picked up vertically or dropped down vertically, it's going to give me the same answer, isn't it? Everybody agree? How about that? So this red graph could give me all of these blue graphs. Could be that one, right? It could be this one, right? Those are telling different stories, aren't they? Sort of different stories. Like if we took, let's say this one right here, let's pick the one that starts right there, and goes, and goes up like this, and comes back down to there. What's the only difference? Instead of starting back here, when I'm going really fast in that direction, I just started it right here, going really fast in that direction. Agreed? Okay, but what if we take the orange one? If we take the orange one, that could get even a whole lot different, couldn't it? Because the orange one, I'm starting at rest, aren't I? Does that make sense? And so that would be like taking the blue one, maybe, and moving it this way, horizontally. You see that? So I got to pick a different color of blue. Thankfully, I have lots of colors of blue. Like taking this thing and putting it over here, so it's going like this, right? My velocity starting off at 0 if I'm this orange one, right? So look at that. I've got all kinds of different stories that can spring from this one fairly boring little acceleration time graph, right? For every red graph I get here, I have an infinite number of corresponding graphs offset vertically. For every offset of the red graph, I've got an infinite number of graphs that could be offset horizontally too. How about that? Is that surprising? Maybe not in a way, because really what this class could be called, at least the mechanics part of this class could be called, is physics with constant acceleration. We're very seldom going to ever deal with anything in this class, because it's not a calculus-based class, that's non-uniform motion. Uniform motion really just means motion with constant acceleration, right? We'll look at some examples, but just not very much, right? But that's a pretty rich topic on its own, because if we start with any constant acceleration, there's a whole bunch of different ways that can manifest itself in terms of the velocities and the positions, right? Make sense? Okay, what we're going to find for calculus types. What we're going to find then, I want you to think about this in terms of derivatives. We talked about this today. Let's go back, ignore all the other stuff, but let's go back to the original blue position graph, the original red velocity graph, and the original green acceleration graph. What kind of function does that look like, the shape? Parabola, which would make it what kind of function?
Quadratic.
Quadratic, this would be quadratic. Okay, now think about, this is kind of a calculus issue. So if you're not in calculus, don't panic. But I really need to say this because it's exactly what we talked about today in calculus. So if that's a quadratic function and we differentiate, think what happens when we differentiate a quadratic. We even mentioned this today. You get a linear, don't you? Right? Because it drops down the order of the polynomial by 1,
And you
right?
do it again, and it's just.
And it's just constant, right?
That makes
How about that?
sense.
Isn't that cool?
Oh.
Yeah. So when and this tells us something interesting and important about calculus. If we start with a specific function and we differentiate, we get another specific answer, don't we? Right? We did derivatives in class today, and every time you were given a derivative to do on the assignment, you got a very specific answer, right? Later on in the year, I'm jumping way ahead here, but I want to kind of plant the seed a little bit. Much further on in the year, we're going to reverse this process, and we're going to do the opposite of differentiation called anti-differentiation. We're going to start with something like an acceleration function, and we're going to work our way backwards by undifferentiating, anti-differentiating. Now that was a different situation there, right? If we started with a function and we took an antiderivative, we didn't get a specific answer. Right? We didn't get one. Every time we take an antiderivative, we get more widely varying possibilities, right? So what's the only way that we could pin this thing down? If I knew that this was the acceleration and I had to determine which of these infinite number of velocity graphs was the right one, I'd have to have an additional piece of information, wouldn't I? I'd have to maybe know, okay, at time 0, what was the velocity? Was it 10, let's say, like it is for the red graph maybe? Or was it 0, like it is for the orange graph? If I had that one little additional piece of information, I could pin this down to a specific answer going from the acceleration upward. Agreed? So let's say that we knew what the initial velocity was. We knew how fast we were going when we started the stopwatch. So we could pin it down to the red one. When I go upwards again, well, what might I need then? There's an infinite number of possible blue graphs, but if I knew what the initial position was, I could pin it down to one of those, right? So just keep that in mind when we get into this stuff later in the year. If we want to work our way up and be specific, we've got to have some additional information to pin down our answer, okay? All right, so, we're getting down to the end. Okay, so then let's maybe throw something up here. I'm going to see if you can make an analogy. Oh, I know one other thing I want to do. One other thing. This is way, way, way beyond what the book is going to do. But that's all right. You guys can handle this. I mean, if you get this, then the other stuff is even easier. So what if I gave you a position time graph that looked like this, let's say? Okay. What do you think that TJ's already got an idea.
Well, I know, I'm taking care of.
So yeah, you know the answer. So you'll be our ace in the hole if we need you. What do you think, Nicole? Can you tell me some places that might be really important if I want to sketch the velocity time graph? Okay, the horizontal tangents, right? So we got these spots right here, right there, and right there. What's the value of the slope at those places? 0. So I know that if I come straight down, those have got to be places where we get zeros for the velocity function. Okay, so now what? Elijah, what's going on here?
It's decelerating.
Okay, well, so yeah, it's high velocity getting lower, right? Okay, and then it goes to 0, and then over here it starts to get more and more negative, right? Is there anything significant if I had drawn this symmetrically about that point right there? What do you think? Steepest point maybe, right? That's where it's the most negative, okay? So that gives us a little insight, doesn't it? So then that maybe coaxes us to believe that this thing might look like that maybe, right? So that point's got to line up with the minimum, the lowest point on the most negative point for velocity. right? It's gonna come back up through zero and get increasingly positive, right? Okay, so TJ, what's the acceleration graph gonna look like?
This is gonna look like, straight line.
So there's gonna be the zero, right? And we're going from where to where with our straight line?
Not be negative.
So we're just doing something like that, aren't we? Right? Okay, make sense? What do you think the shape of that curve is?
X cubed.
It's cubic, isn't it? Yeah, so that's a cubic. So its derivative would be quadratic, and that derivative would be linear. How about that? Make sense? Okay. One last thing. This is where we'll leave off. That's a lot of stuff, but keep in mind now, we said that acceleration is to velocity as velocity is to position. We only have one kinematics equation, one wimpy kinematics equation to work with. We got to get some more. So that's what we're going to be working on the next couple of days, is getting some more and practicing using it, right? So this is the one that we have for now. We know that position equals what? Initial position plus VT. Oh my gosh, is this something like a big deal here? Hey. Oh, okay. Okay, sounds good. Yep. Okay. Okay, back. Back. Okay, so what do you think we could say about velocity and acceleration? Remember we said velocity is to position as acceleration is to velocity.
So would it be at the acceleration level?
Okay, initial velocity. How about that? That's true. We got another, just by following our analogous relationship there, right? We get a free kinematics equation, okay? That's probably a good place to stop. Is that enough to think about for one day? It's a lot of stuff, isn't it?